so much, Professor Sogo Mazu, for the very systematic and elaborative presentation. And thank you, Mr. Husnu Wijaya, for leading and guiding the discussion. Ladies and gentlemen, we're going to proceed to the third plenary session. The third plenary session will discuss a paper entitled Advanced Materials and Heterogen Catalysts by Professor Dr. Hadi Nur from University Technology, Malaysia. And we're going to invite Associate Professor Dr. Muladi as the moderator. Mr. Muladi, over to you.
Okay, thank you, host, Ms. Rahmadi. Good morning, ladies and gentlemen. It's a pleasure for me to introduce our third keynote speaker today, Professor Dr. Hadi Nur. Good morning, Professor.
Pagi.
Pagi.
Pak Maladi.
Yeah, very good morning. Yeah. Okay, Prof. Hadi is professor and also institute director at Ibnu Sina Institute for Scientific and Industrial Research, University Teknologi Malaysia, UTM. And he is also a young professor at Universitas Negeri Malang. Yeah, Prof. Hadi is going to talk to us about the structure properties relationship in the proton conductivity enhancement. So this is interesting topic actually in the sustainable nanomaterials, yeah, in which we should all be deeply interested. So before we proceed with the presentation from Prof. Hadi, let us watch his curriculum vitae. Okay, thank you. We have 45 minutes, Prof, for us. So you have presentation in 30 minutes and another 10 minutes for Q&A. So during this presentation, the audience can ask questions through the chat box, and I will read out in the QA session. Ladies and gentlemen, please join with me in welcoming Prof. Hadi. Prof. Hadi, time is yours.
Jelas ya, slide Pak Meladi ya?
Ya, sudah nampak, Bro.
Sudah nampak ya? Oke.
Sudah nampak.
Oke. Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera. I would like to thank the committee, Universitas Negeri Malang, for inviting me to deliver a talk on this conference. As mentioned by Pak Mulyadi, currently I'm a director of one research institute at UTM. That is Ibnu Sina Institute for Scientific and Industrial Research. And at our institute, this is the multidisciplinary subject in this institute is from the mathematics, physics, social sciences to technologies, and also the humanities. This is our noble task to contribute to the society on a national and global scale. There are 6 research centers under Ibnu Sina Institute, UTM Big Data Center, Center for Sustainable Nanomaterial, Center for FIH Research in Science and Technology. Di sini ada Ustadz dan Ustazah ya, di sini di C4 ini, and also UTM Center for Industrial and Applied Mathematics, Laser Center, and Center for Lipid Engineering and Applied Research. It can be seen that our institute covered the field. I said that this is from data to the wisdom. This is the facts and figures of the Ibnu Sina Institute. Currently, in terms of the number of staff, we are the largest institute at University Technology Malaysia. Okay, let's start with the topic of this presentation, that is well-aligned titanium dioxide particles and polybenzimidazole membrane prepared under magnetic field, structure, properties, relationship in the proton conductivity enhancement. Maybe we have seen a character from the story about the X-Men. The X-Men films, an antagonist character, namely Magneto. And we know that this man used magnetic power, and he wants to rule the world with his magnetic power. This is our inspiration in doing this research. The magnetic field is a potential power possessed by the Earth and is rarely used for the synthesis of materials. Based on this, we try to use a magnetic field potential in our research, namely to control the formation of materials, especially for the synthesis of the inorganic materials. In this study, magnetic effects were used for the two research topics, namely shape control titanium dioxide containing 5Cb photocatalyst and low magnetic field induced aligned polybenzimidazole membrane. If we look at the relationship between the structure and properties of semiconductor material, such as titanium dioxide and photocatalyst properties, the role of the electron-hole recombination needs to be considered. One hypothesized that electron-hole recombination can be reduced if the material used is one-dimensional material. This is quite logical because in one-dimensional materials, the probability of the electron and hole to meet will be reduced because they are limited by one-dimensional space. The probability will increase if we use 3D and 2D materials. This hypothesis has also been put forward in a paper published in the nanoscale research, which states that the well-aligned orientation will provide a good electron diffusion due to the molecular alignment of the titanium dioxide photocatalyst. To prove this, we attempted to synthesize one-dimensional light material by using magnetic field. The use of magnetic field in the synthesis of inorganic material has been reported by researchers from Waseda University, Professor Kuroda in 2005. They used a very strong magnetic field of the 12 Tesla. And they managed to align mesoporous silica using magnetic field. However, I did not find the continuation of the research from Professor Kuroda research group. This is the only paper from this research group that use magnetic field to control the structure of materials. However, we still see the opportunities for magnetic field to be used for the material synthesis. In 2012, my research group succeeded in synthesizing well-aligned titania using cetyl tetraammonium bromide, or CTABR, as a structural aligning agent. This paper was published in Chemistry Letters in 2012. The results are quite interesting. However, we still have not been able to elucidate the cause or the reason of the disalignment because there are no material with high enough magnetic properties to be used in the synthesis procedure. The magnet used to synthesize this material is 9.4 Tesla. We use a magnet derived from the our NMR magnet. We took initiative by choosing CTABR, as a structure directing agent with the materials that has good magnetic properties, namely liquid crystal. Our hypothesis is a well-aligned titanium dioxide with a very high length to diameter ratio could be synthesized under magnetic field by sol gel method with the liquid crystal as the structure aligning agent. The synthesis process is very simple, namely by placing 4-cyano for phentyl-phenyl, this is a liquid crystal, water, alcohol, and tetrabutyl orthotitanate in homemade magnet apparatus. The composition, the precursors is varied to get the best result. Yeah, and this is very simple procedure, and this is the result obtained. It appears that with hot magnetic field, and the liquid crystal, well-aligned solids do not form. Yeah, and under the magnetic field, well-aligned, the magnet use well-aligned is a form. And with the magnet use is relatively small, yeah, which is 0.3 Tesla. This is a synthesis procedure of the well-aligned titania containing liquid crystal. The first step, 5Cb liquid crystal was mixed with the 2-propanol and distilled water. Then the TBOT, that is the source of the titanium dioxide, was added into mixture and leave it dry under magnetic field at room temperature. And then sample will be completely dried and hydrolyzed after 3 days. The position of the sample, yeah, from homemade magnet apparatus also has an effect because there is a magnetic field line form. Yeah, this is the magnetic line. If we put under the magnet, or if put the iron powder here, we can see the magnetic line. And the location of the sample with respect to the direction of the magnet affects the formation of the material. Yeah, this is the result of the sample is placed on the top of the magnet in true plane direction. Yeah, true plane direction. And we found that this interesting result that if we put the sample in the true plane direction, yeah, and if we put the sample in plane direction, yeah, in plane direction of the magnetic field, we can see that here, yeah, of the rambutan-like materials, yeah. The rustling sample is like rambutan-like material, where the hair of the rambutan is the liquid crystal, and the fruit is the titanium dioxide. This is an illustration of the effect of magnetic line shown by SEM images of titanium dioxide 5Cb particle synthesized at the different position of the magnet bar. Yeah, we put the sample of the different position where the magnet direction is the true plane or in plane. Yeah, and this is the SEM image of titanium 5Cb before and after the washing process. Okay, now we need to think that what is the main factor? Yeah, the main factor contributing to the successful alignment of the material with the magnetic fields is the hydrolysis process of the precursor. Yeah, so consisting of the titanium butoxide and a mixture of water and alcohol. We try to control the hydrolysis time as long as possible, so that the material has time to align with the magnetic field. If the hydrolysis process is fast, then there is no chance of the material for a self-assembly to align with the magnet. In this case, it took about 3 days for the hydrolysis process so that the titania liquid crystals were aligned under magnetic field. So the key is that for this experiment is that the hydrolysis time. This is the relationship between the well-aligned structure and the direct current electricity. It can be seen clearly that the voltage and current of the titanium dioxide 5Cb synthesized under magnetic field produce a higher slope than without the magnetic field. The whole effect also shows the same thing. Yeah, titanium dioxide 5Cb sample synthesized under magnetic field, here the blue one, give the higher Hall effect when compared to the without magnetic field. Yeah, this is the orange one. These are the SEM images of the sample synthesized by magnetic field and without magnetic field. Yeah, it is clear that the alignment occurs. Yeah, for the sample we placed under the magnet. Yeah, is aligned in the direction of the magnetic field. The photocatalytic activity of well-aligned titanium liquid crystal show a higher activity than the non-well-aligned materials. And this is a very interesting result because this proves the hypothesis that one-dimensional light material can increase the photocatalytic activity of the material. So previously we said that, oh, maybe the one-dimensional materials have the good photocatalysis. We need to synthesize the well-aligned materials, and we need to prove that is it give the high photocatalytic activity or not. Yeah. This is a photoluminescence spectra of the titanium dioxide 5Cb sample synthesized under magnetic field and without magnetic field. It can be seen that the sample synthesized using magnetic field show a new peak here at the 350 nanometer. This is due to the unique charge transfer of this material caused by interfacial interaction between the titanium and the liquid crystal. To elucidate this, we use DFT, density functional theory, to describe to explain it. And this is the result of the DFT calculation. It can be seen that there is a charge transfer from the valence and conduction bands from the liquid crystal to the titanium. This can only be done if there is an interfacial interaction between the liquid crystal, yeah, and the titanium. Okay, now we change the topic for the low magnetic field induced aligned polybenzimidazole. Yeah, this is a membrane. This is a schematic diagram of the temperature proton exchange membrane fuel cell, where the main component in this fuel cell is the membrane. Yeah. The membrane is placed between the anode and cathode, and which contains platinum, which acts as a catalyst. Yeah, which acts as a catalyst. And this is a possible structure of the phosphoric acid dope and ferrocene dope polybenzimidazole membrane. Yeah. And polyimidazole membranes attract attention because of this material has a high thermal stability, high chemical stability, and also low cost. However, the pristine polybenzimidazole is a poor proton conductivity and needs to be modified by adding additive or acids. Yeah. Usually, to improve the conductivity, we need to add the additive, yeah, to the polymer matrix. To increase the efficiency of the proton exchange membrane, several strategies have been carried out. Yeah. Among them is by adding nanoparticles and also by using electrospinning to produce a random aligned structure. Yeah. One interesting method is to use particles that can align with the magnetic field, so that the proton conductivity increase. In this study, we use polybenzimidazole, a material that is considered a potential proton exchange membrane. So the topic of this project is to answer the questions: how to control the orientation of the polymer structure of polybenzimidazole under magnetic field. Previously, we have experience to align the titanium particle by 5Cb liquid crystal, but in this project, we don't use liquid crystal because liquid crystal is volatile. It starts to evaporate at the 70 degrees Celsius. This is the material we use in this project, namely ferrocene modified polybenzimidazole. Ferrocene carboxylic acid was dissolved in the dimethyl acetamide and added to the polymer membrane. This is polybenzimidazole. If we look at the direction of the polymer chain arrangement, it can be hypothesized that the alignment of the chain can be controlled by applying a magnet to the membrane, yeah, with the in plane direction. Here's number one, in plane direction here, and through plane direction, yeah, through plane direction. So we need to think that how we can align the membrane by putting in our magnet. Fabrication of polybenzimidazole is done by casting and followed by doping using the phosphoric acid. Yeah, is a very simple methods. And we use homemade magnet whose magnetic strength is a 0.3 Tesla. And the sample is placed between the north and the south poles of the magnet, so that it is expected that the polybenzimidazole membrane can align with the magnetic field. This slide shows the fluorescein functionalized polybenzimidazole membrane preparation. The membrane was cast with the fluorescein carboxylic acid solution. Yeah, the solution was poured into the glass plate and cast with the stainless steel scraper and applied a magnetic field perpendicular. Perpendicular means that through plane direction and also in plane direction to the plate with a strength of 0.3 Tesla at the room temperature. Then the cast fluorescein polybenzimidazole membrane was dried in an oven and the solvent slowly evaporated and the light brown membrane was formed. This is the picture of the membrane produced. Yeah, the digital photograph of the series of the polybenzimidazole base membrane show uniform and homogeneous with the brownish yellow color. Yeah, it is visually observable that with the increase in the fluorescein carboxylic acid content, the opaqueness increase. Okay, this is WOM, this is without magnetic field, and WM is the with magnetic field. Okay, the visible pi stacking of the aromatic ring, yeah, because we know that the polybenzimidazole, they have a lot of the polyaromatic ring, yeah, in the structure, yeah. The pi stacking of the aromatic ring of the polybenzimidazole microstructure cast under a magnetic field is demonstrated in this slide. Yeah, it is suggested that the pi stacking result in a decrease in the absorption intensity of the magnetic field treated polybenzimidazole membrane. Yeah, you can see here that the visible pi stacking or aromatic ring of the polybenzimidazole microstructure cast under the magnetic field. This is the effect of the magnetic field in plane direction. Yeah, by ion filling, then its corresponding cross section of the ACM image of the PBI membrane. This is the ACM image of the cross section of the membrane, and it is confirmed that the presence of the ordered polymer structure. Yeah, it's very clear here from the ACM image. And from the analysis of ACM, the effect of the magnetic field in the true plane direction was also confirmed. Yeah. However, because of the limitation of the imaging facilities, we know that the ACM image is only micrometer scale of the magnification, and this is cannot strongly support, yeah, this formation of the aligned structure for the membrane. So we use the atomic force microscope, yeah, and atomic force microscope is used as a supporting evidence of the microstructure orientation. And the AFM topography that shows that is very clear, shows that the effect alignment in the plane direction. You can see here that we can see the alignment of the polymer, yeah, under the in plane direction. It's very interesting result, is, yeah. And the the effect of the alignment in the true plane direction was also shown by the AFF. Yeah, it shows that the small spike here, we can see that small spike. Yeah, are uniformly and densely distributed in membrane surface, which indicates the successful alignment of the polymer microstructure even at low ferrocene content. Please remember that the ferrocene have the iron, yeah, so that this spike is reflect the content of the iron in the ferrocenes. It can align with the magnetic field.
Oh yeah.
We found that the higher content of the ferrocene in this study is likely to facilitate the degradation of the membrane. Yeah, and this is because the ferrocene that possess an electron donor acceptor conjugated structure. Yeah, this is the ferrocene. They have the electron donor acceptor conjugated structure with redox reversible characteristic, could enhance the generation of the free radical. Yeah, free radical from the activation of the hydrogen peroxide. And this phenomenon is vulnerable to oxidation or degradation. So in the shorts, we can say that the presence of the ferrocene can promote the polymer degradation by oxidation reaction. This schematic diagram of the hydroxyl and peroxyl radical attacks the ferrocene polybenzol membrane in the Fenton reagent solution. We know that the Fenton reagent solution is that containing iron and the hydrogen peroxide. Yeah, and radical were continuously generated from the peroxide via various ion cycle. Yeah, between the two oxidation state here. So the radical generated will readily attack the polymer in the membrane solution. That is one of the weakness of the use of the ferrocene as the aligning agent in this research. And proton conductivity, yeah, is one of the most important factor influencing membrane performance, especially in high temperature proton exchange membrane fuel cell. The proton conductivity of the polymer benzimidazole based membrane were measured in plane direction and also through plane direction at different temperature. Yeah, and this is we show there in this slide. Yeah, under the hand-reduced condition, the proton conductivity increased with the increase of the temperature. You can see here that increase the temperature, the conductivity is increased from 100 to 180 degrees Celsius. In addition, all the polymer benzimidazole based membrane have better through plane conductivity than in plane conductivity. Yeah, this is a better conductivity in the through plane direction of magnetic field compared to the in plane proton conductivity. We know that the membrane here we put in the magnet with the through plane direction and the in plane direction of the magnetic field. As expected, the highest through plane proton conductivity, that is 0.028 Einstein per centimeter minus 1, was obtained for the polymer membrane at 180 degrees Celsius. Yeah, 180 degrees Celsius. And the acidic anion of the phosphoric acid and the imide functional group size of the polybenzimidazole chains mainly contribute to the increase in the proton transfer between the acid-base interaction. However, at 140 degrees C, here in the true plane proton conductivity, a sudden decline, yeah, in the proton conductivity was observed. And this is due to the leaching of the acid during the test through the evaporation process.
Excuse me, Prof. We have 3 minutes now.
Okay. Yeah, from the Arrhenius plot, yeah, above, the calculated activation energy associated with the proton transport in the polymer membrane are shown in this slide. The result provide a valuable information about which conduction mechanism is responsible for proton transportation. The activation energy for proton conduction in membrane is quite similar with around 10 kilojoule per mole respectively. This indicates that a similar proton conduction mechanism dominates in the both case here, which is known as a vehicular mechanism. In addition, the higher activation energy of polymer sample with around 15 kilojoule per mole and more than 15 kilojoule per mole here signifies that the Grotius mechanism is the dominant proton conduction mechanism of the membrane. We know that the Grotius mechanism exhibits activation energy in the range of 14 to 40 kilojoule per mole. Okay, and this shows that the proposed proton conduction mechanism based on the Arrhenius plot polymer-based membrane. It is suggested that without the addition of the ferrocene moiety in the polymer matrix, the vehicular mechanism here, you can see that here mechanical mechanism exists as a dominant transport mechanism of the membrane. This indicates that the proton conductivity is possibly contributed from the polymer matrix. After the orientation of the polymer changes toward the magnetic field's direction, the activation energy decreases, and this shows that a line proton exchange could enhance the proton conductivity of the membrane with the increase of the temperature. It is also suggested that after the addition of the ferrocene, the dominant proton conductive mechanism is a Grotius mechanism. And this is the slide, the last slide. This is a summary of the structural properties relationship of the polybenzimidazole base membrane. Yeah, based on this research, the relationship between the addition of the ferrocene and the magnetic field treatment on the polybenzimidazole membrane can be observed clearly. Yeah, without magnetic treatment, the membrane with the high number of the ferrocene shows the lowest true plane conductivity. Nevertheless, once the magnetic field was introduced, the membrane shows the highest conductivity. Thus, this creates a continuous pathway for the proton conduction and increase the proton conductivity through the membrane. So this is the conclusion that we can align the polymer, polybenzimidazole in this case, with the magnetic fields, so that we can increase the proton conductivity to give the better performance of the fuel cell. And lastly, I would like to thank my PhD student who worked on this project, Dr. Nur Izzati Abu Bakar, with the project of SEP control titanium liquid crystal photocatalyst, and Nur Arbani Sen with the project magnetic field induced aligned polybenzimidazole. Okay, this is the last slide. This picture was taken in 2014. All the students in this photograph were graduated, and this is Pak Nur Hadi, currently now professors at Universitas Mula Warman. This is Dr. Umar, currently a lecturer at the Universitas Negeri Padang. Ini Bu Samsi, juga dosen di Universitas Negeri Padang. Safrina sekarang dosen di UTM. Sheila, also staff at the Department of Chemistry at UTM, and the others. This is Fatemeh, Suku from Iran. This is from Iraq, Ali from Iraq, and lastly, I would like to say wassalamualaikum warahmatullahi wabarakatuh. Oke, 30 menit Pak. Saya curi waktu 1 menit, 31 menit.
Oke, Pak.
Oke, terima kasih.
Very interesting presentation, and also plenty of valuable knowledge. Now, I invite the audience to ask a question, please.
Oke, tanya apa saja. Di luar topik ini pun oke.
Ya, sila.
Silakan.
Ya, silakan.
So please.
Anybody? Questions?
Mungkin nggak ada ini Pak. sudah lapar semua ini.
Belum lah.
Belum ya.
Masih pukul 10 ini.
Oke, sebelum ya.
Ya. Okay, Professor, I'm sorry. Yeah. Maybe the audience have understand what your present. Yeah. So there's no question for you. Sorry. Yeah. Thank you very much. And yeah. Thank you again for Prof. Hadi Nur. Yeah. For the knowledge that you have shared, and also maybe the audience will contact you privately outside of this conference, yeah, directly. Okay, thank you. Now it's time for giving certificate. Keynote speaker, I-CoRE 2021 to Professor Dr. Hadi Nur from UTM Malaysia.
Ya, terima kasih.
Oke, saya buka masker dulu. Sebab saya ada beberapa kawan ini di ruangan, so saya guna masker. Okay, thank you, Prof. Hadi Nur, for your participation, so for sharing the knowledge in this second I-CoRE 2021. Have a nice day, Prof. And stay safe and healthy. See you at the other occasion. Thank you very much. I turn back to the host, Ms. Rahmati. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Salam warahmatullahi wabarakatuh.
Thank you so much, Professor Hadi Nur, for the very insightful presentation, and thank you for Mr. Muladi for